All right, 121 students. Let me get started here on the second solution one. For those of you who are paying attention, I just did number 2. I'm going to do number 3 here. And I started to read it here, and I went ahead and said this was unnecessary, a period of 1 day, when they say it's a geosync orbit. In fact, a planet would look something like this. Let me call this capital M for the mass of the planet, and then I'll just use an M, and maybe I'll call it M1 for satellite number 1, because this one goes on to talk about satellite number 2 being a little bit further out here. In fact, then maybe I'll just read it here with you now that I read it. It says satellite 1 is in a geosync circular orbit around the Earth. And then it says, so then it has an orbital period of 1 day. And so, again, not necessary. That's what a geosync orbit means. A geosync orbit means it is out here far enough that as it goes around, the Earth underneath rotates and they kind of stay together. And so the satellite is always over the same location of Earth or whatever planet, because we put geosync satellites over, say, Jupiter, so we can study the weather patterns on Jupiter. But this one's talking about Earth. And so this would be one day. Okay. And then they go on to say here that satellite 2 circular orbit is a little bit larger than the circular orbit by a factor of 1.82. Okay, so I'll call R2 equaling 1.82 times R1. Okay. But our question then is saying by what the orbital period of satellite 2 is how many days. And so since it's a little further out, it should be more than 1 day. And it looks like the correct answer is 2.46 days, and the wrong answer is 1.82 days. Okay. But let me kind of work this out. The new thing for this chapter is what is called Newton's universal law of gravity. And so let me not put a 1 or a 2 here for a moment. Let me just say that I have a satellite, I have a planet, and some radius. Because if you take this force of gravity, and that's the new piece for this semester, and you couple it with what we learned in Chapter 5, that objects going in a circle have to have this much centripetal force, you can set the two equal to each other. In fact, even cancel 2 items. And so you get velocity squared, and you can see that the velocity has something to do with the radius. That's why I was saying satellite number 2 is going to have to go a little slower, because you can see here the radius would be a little bit bigger, and so therefore it goes slower. And in fact, not only does it go slower, but it also has to go further distance because it's got a bigger circumference. And so for both of those reasons, satellite number 2 is going to take longer, and that's why I was saying I expect this to be greater than 1 day. And both of these, the wrong answer and the correct answer, are more than 1. So as long as I had something more than 1, at least I would think I'm kind of on the right trail. All right. Now, here's where I'm going to take advantage also of, wow, this goes way back to Chapter 2. I'm just going to say if you take the distance and divide it by time, which in this case, the satellite would go in a circle, so 2 pi r, and then what we call the period of the satellite, that is the velocity of the satellite. And that's kind of useful, because if I take this number and I square it, I get a 4 squared, I get a pi squared, I get an r squared, and I get a period squared. And then maybe if I cross multiply, so I don't have to deal with fractions here, I'll get a g times m period squared, and then I'll get a 4 pi squared over r cubed. And so there's a mathematical relationship between the period squared and the radius cubed. And what's interesting, I think, in history is Kepler discovered that. He realized that if you took the radius cubed and you multiplied it by the same number, and he didn't really understand why and where that number originated from. So he didn't have the luxury we have today of Newton's laws. So Kepler was before Newton. He just realized that if you took the radius of each of the planets, and of course he was dealing with the sun and the planets orbiting the sun, not the satellites orbiting the Earth. But it was the same basic idea. If you took those distances and you cubed them and you multiplied by the same number, you got the period squared of each of the known planets. And he was like, huh, that's very interesting. Very, very interesting. But that helped Newton then on his way to come up with the universal law of gravity. All right, now let's apply this idea that the period and the radius are mathematically connected, and let's do it for each of the satellites. So if I put like first satellite squared, and then I have a 4 pi squared gm and radius cubed for number 1, and I write that same equation but apply it to satellite number 2, I get these two equations, and when you then divide one equation by the other, you would get period 1 over period 2 squared over here on the left-hand side. And on the right-hand side, this constant that I said Kepler, figured out, but like had no idea where it came from. He had no idea that it was made up of the universal gravitational constant, in this case the mass of the sun, although for us it would be the mass of planet Earth. Anyways, there is this mathematical connection, and that's going to be the key to the problem right here. So this is really where we want to start our calculation, because remember earlier on they told us right here this ratio. So this would say that if I left R1 in the top and replaced R2 with 1.82 R1 and I cubed it, I would have the ratio of the times squared. Of course, the R1 would go away. Now, to get just the ratio of the times without the square, I need to take the square root. So I'll take my 1 over 1.82 raised to a power of 3 and then take its square root, which means a power of 1/2. And so that's 3/2 power is this ratio. And again, I'm treating number 1 as the closer one, and so we know this right here is 1 day. So I'll put T1 equals to 1 day. So T1 equals to 1 day, and I'll do it in units of days. And then I have T2 is what we're hunting for. I believe that was the question. Yeah, the orbital period of satellite 2 is what in days? So I'm looking for that. And then this is just a number. Now, granted, I have to do a little bit of work to get that number. Why don't I start with this inside piece and go 1 divided by 1.82. And then let me raise it to a power of, and I'll just call that 1.5. Well, for you guys, since you're watching, I'll go 3 divided by 2 just to kind of show you. Don't, go ahead and take advantage of the fact you can do fractions and the exponent on your calculators there. And it looks like I got 0.407, so 0.407. Or finally, to finish this off, let me bring the 407 underneath there. So it's 1 divided by that last answer. And it looks like about a 2.46. And remember, I'm in units of days, and I guess that would match right here. Okay. Okay. So there's the solution to number 3. Hopefully that helps somebody.